Okay, thank you, Daniel, and good morning or good evening, everyone. And so welcome back to the second lecture. And I'm going to start off with a question that was raised yesterday at the end of the first lecture. And I just added a couple of more slides that I didn't have preliminarily. As an answer to the question that was raised, I was asked what are gerbes. So as a whole, they could be just a course on their own. So I'm not going to be too pedagogical with that, but I'll just give you an idea of where to search for the literature if you want to dig more into that topic. So as a preliminary to gerbes, I would say first concept is that of sheaves, which are also known as étale spaces. And they're basically defined over a topological space that I here call B. And the sheaf is an object, this E, such that the map P, E to B is a local homomorphism. So once you've defined a sheaf, the categorical version of this definition gives you that of stacks. And once you have a stack, then you can define gerbes, because this is also very technical. I understand that, but I can't go too much in detail because I would lose too much time. But if you have an infinity one topos, then a gerb is an object such that it is one truncated and one connected, which means that is a gerb that is a stack that is locally like a d-looping of sheaves of a group. Now, this notion of d-looping is something that was there's a vast literature in this, and the leading person, I would say, is Lurie. You will find lots of maths papers in this regard about d-looping spaces. And I would suggest you to search for that for anything that you want to understand much more in detail. But this is all that I can say for the moment. Because as I said, this is a very large topic and I couldn't go too much in depth. I don't know if the person that asked me is in the audience now. If so, I hope that this is enough, but I hope that you also understand that this is not, this goes a bit beyond the main aim of the course on its own. So I would suggest that person or whoever is interested to look at the papers in the archive by Jacob Lurie, and you will see a lot of papers written on d-looping spaces. And he also wrote them together with Michael Hopkins, Daniel Fried, and Konstantin Telemann. These are four people that wrote a lot of papers together, and they're all about this topic. And it's closely related to what I started explaining yesterday, so I would strongly suggest you to read them if you are interested. But I can't go too much in detail on that for the moment. So I hope this answers the question. So today I want to continue with the topic that I started off describing yesterday, which was the categorical description of quantum field theory. So we did yesterday I introduced the notion of relative field theories and how you can turn a relative field theory into an absolute theory by acting on the boundary conditions. So you basically select a subgroup. Sorry, maybe there's a message in the chat. Okay, you're welcome. Okay, so there's I said yesterday there's I discussed how to turn a relative theory into an absolute theory, and we looked at the examples of sigma models and gauge theories, which are just in the context of just one particular interaction. Okay, so I didn't discuss anything involving more than one interaction in that setup because that is very it's complicated and nobody knows exactly how to deal with that at a categorical level. So I'm not going to explain how to, for example, realize the standard model in the symmetry topological field theory setup, because that's something that nobody knows how to do yet. And that's the main purpose, the objective of this method that has been developed in the last 3 years. So What I will do instead now is to go more in depth in the maths that underlies what I explained yesterday. So that's why this course is meant to be for mathematicians, because I really want to give the mathematical insights that lie behind the physics. So today is going to be very much based on the categories and on the maths, but we always try to keep in mind the physics that is behind that. So I will always try to underline and highlight where connection with physics emerges. In particular, today we're going to appreciate how the categorical description automatically leads to the notion of charges. And as I said also yesterday, charges are very important because if they give us a notion of symmetries in the theory, and they automatically also tell us about the choice of the boundary conditions of the fields that live in our theory. So altogether, they are powerful data that if we can access, then we can write things like partition functions, and from them we can calculate the correlation functions that then are in turn used for predicting what you would expect to achieve from scattering amplitudes. Okay, so having said this, now we start with this first part, which is gauging categorical structures. So when I explained yesterday how to turn a relative theory into an absolute theory, I said you need to select some kind of, you start from a gauge group, that is the symmetry, the global symmetry of your theory, and you select a subgroup of that original gauge group, and you quotient with respect to it. So you basically gauge that subgroup away. And that gauging allows you to turn the theory into an absolute one. So what does that gauging mean from the maths point of view? Okay, so gauging is usually associated to a physics term, a physics notion, okay? So in the context of maths, by gauging, we mean the following. So we start from a fusion category, this curly G, and there's an associated fiber functor, this curly F. So this functor selects nvec as the image of a gauged algebra that lives inside curly G, which corresponds to the projection of the identity. So what this means is the following. We start from the symmetry TFT, so I'll go back a few slides to something that we saw yesterday. I know that you already have access to these slides, so you can look at it also yourself. So you have sigma. We're basically looking now at how to determine the gauging from the bulk, okay? Because yesterday I said everything that is in the bulk has notion of what lives on the boundary. So the resultant theory that lives on F raw here is basically a result of the topological action of the pair sigma rho acting on F tilde, which is the relative theory. So if we want to achieve a specific absolute theory, we need to select appropriately the topological data sigma rho. And if we want to gauge the theory, so gauge a subgroup, we have to act suitably on this topological data. So yesterday, somebody asked me, what is the categorical structure? And I thought that he was asking me the categorical structure of sigma. So if you look at that, the categorical structure of sigma is actually made up of topological things, so topologically extended objects. We will see this in a particular example later on, but just to give you an idea, if sigma is something that is like 7-dimensional, you can imagine to have objects that are 3-dimensional living in it, and they are like extended surfaces. And those surfaces are allowed to intersect each other. For example, they could form some kind of hop links. And the intersections in turn are going to define the morphisms in between the surfaces. And in turn, the morphisms can be intersecting each other to get two morphisms and so on. So the pattern that these defects determine in the bulk sigma are basically telling you the nature or the particular choice of the gauge group that you've chosen for the theory, for the resultant theory that you want to study. So if you want to gauge away part of that gauge group that defines the global symmetry of the theory, then you need to act appropriately on those defects, which means, for example, some of the defects might be trivialized. So going back to the case of the Hopf-link, if you know what it is, it's basically two rings that are linking each other, okay? So that is a non-trivial configuration, but you could think of trivializing one of the two rings such that you end up having just one ring. And that could be associated to a particular gauging that you choose to do. And the impact of that on the spectrum of the theory, so the charges that result in the absolute theory, are going to be dictated by that trivialization. So basically, the important thing is to understand whenever you perform the gauging on the group, that implies some trivialization of the defects that live in the bulk sigma. So having that in mind, the trivialization means that you need to define what the identity is, because by trivial I mean actually the identity, I don't mean zero, okay? So what I have here is basically this function, this functor f, which is called the fiber functor, is telling me what I want to trivialize, okay? And the gauging is this process of choosing the subalgebra of defects that live in the bulk sigma, such that that subalgebra is trivialized. So this is what I call, or is called, the moment map. This mu is basically a map that goes from the fusion category, curly G, to this subalgebra AC, which is the algebra that I want to gauge. So it's the algebra of topologically invertible defects that live in the sigma bulk, okay? And they are going to be sent to the identity in the new theory that I end up with, okay? So that's what I mean by trivializing. So in pictures, this is easier to see. So say that we start from the bulk. So this, I'm just drawing the sigma, okay? I'm just drawing sigma here. I'm not drawing the boundary theories for the moment because I just want to give you an idea of that. So the bulk is basically made up of many constituents. It's a category, okay? But you can think of this category as building up an algebra, okay? So I call this algebra A, and A encodes everything. It's got objects, it's got morphisms, etc. Now, this is the starting point, okay? It's associated to some gauge group G. Now, if I want to gauge away some subgroup, then I need to define some, I need to define this curly G. So I need to define this N fusion category of objects that lives in sigma that needs to be trivialized, okay? So doing that automatically gives me the notion of a norm element, this capital N. What this norm element is, it's basically the sum of over all the elements of the fusion N category that I've chosen for the trivialization, summing over all the maps mu acting on these elements. So basically, I'm building this these black lines. These black lines are nothing but all the objects and morphisms that live in A that I want to trivialize to the identity in the new theory. So they build up this network that you see here. It's totally random. It doesn't have a well-defined path, okay? And this is because N, this norm element, is basically each point of the black line is this N. And it's a categorical idempotent, which means that you can take any combination of it, and it always gives you the same thing as a result of the gauging process. So basically, it makes no difference to draw it as in this middle picture or on the far right. Okay, so in the end, you can condense these lines together as being just one unique line that you see here in the middle. And this is the bulk in the resulting theory once you've performed the gauging with respect to the N category curly G that you've chosen to condense and bring to the identity. So this is the picture that gives you that actually shows you what happens in the bulk and why this affects the spectrum. It's clearly seen because actually you are acting on the topological objects and the category that lives in the bulk, and that effectively gives you different objects in the bulk of the topological theory that lives with respect to which the relative theory is on the boundary. So essentially, we can say that an absolute theory that I call curly T is in one-to-one correspondence with a triple of maps. And these maps are, one is the fiber functor, one is the moment map, and the other is the Drinfeld center. So these three maps are crucial in whatever follows next because they essentially encode all the information that you need. If you know one of them, one of these three maps automatically gives you the other. So that's why they're so important. And they are identified with the notion of a partition function. So if you know them, you know the partition function of the absolute theory. So that's why they're crucial in a physics point of view. So what is the Drinfeld center? I didn't say this before, but the Drinfeld center is defined as being the endomorphism of the identity. So that's why you see this identity is actually the identity of the theory once you've performed the gauging. So that's why it's important, and it encodes the notion of what you've turned into the identity once you've performed the gauging. So this identity is a highly non-trivial object in principle. It can be an algebra on its own with its own automorphisms. So it's a very intricate object, and it can be very interesting. And that's exactly why it's so important. Okay, it can be also trivial, obviously, but in the physically most interesting cases, it's highly non-trivial. And this endomorphism is basically a home of the identity to itself by definition. And this is also known as the Hochschild cohomology. And we will see this later on will come up. So just take it as a definition for the moment, and we will see this explicitly in concrete examples. So the main takeaway that I would say of this from the point of view of the categorical gauging is the main thing to look for is the identity. So we always need to keep track of the identity, the notion of the identity in these categorical structures and how the gauging process affects the notion of the identity, because that's a crucial thing because it gives us the Drinfeld center, and according to this correspondence is in one-to-one there's a one-to-one identification with the complete notion of an absolute theory and its corresponding partition function. So this is crucial to know. Are there any questions up to now? I don't see anything in the chat, so I will go on. So the key points so far, I didn't say exactly yet what ring homologies are, but we will see them later. But two important things that I would say for the moment is to bear in mind that we always need to keep track of gaugeable algebras. Okay, so we need to see how much we can gauge of the theory that we already have and how to define this moment map mu. And once we have that, then also to understand how to embed the gauged algebra, because the embedding obviously tells us if we can relate the theory that we've obtained after gauging with some other theory that we could achieve by some other gauging. So the reason why this is important is because in physics, in addition to symmetries, there's the important notion of dualities. And in string theory, dualities are crucial because you might have heard that they relate different string theories together. But apart from that, there's also other kinds of dualities, such as mirror symmetry, that is related to different sectors of the theory in question that might swap roles if you take different theories that are related by some kind specific kinds of dualities. So if you try to understand how gauging affects the algebra of the resultant theory and how to obtain different theories with different algebras from the same mother theory, you might be able to study these dualities in this from this categorical point of view. And we will see the explicit example of 6 dimensions n equals 2 superconformal field theories that we know to give rise to dualities, a rich web of dualities actually, in between lower dimensional supersymmetric field theories. So this is, and you can do that, you can study that by means of this categorical point of view, which I believe to be very instructive to, and should be definitely be extended in more general setups. And it's currently a broad area of research by many experts. So I would really like to go into that in depth later on in this course. So now we turn, as I mentioned earlier, to the notion of charges, because as I said, this is crucial. If you know the charges in the theory, then you can identify the spectrum of operators, and from them you know the boundary conditions, and then you can also have a well-defined path integral. So this is going to be very mathematical, but still with a physics point of view behind. So we start from the definition of a defect fusion category. So first of all, a category is said to be monoidal if it comes equipped with this bifunctor. So you compose the category with itself and it gives you back the same category. So if C is semi-simple, then the tensor product of any two simple objects in it are going to be given you a sum over all the irreducibles of C of n, this is some kind of number, times z, okay, where z is also a simple object in C. And these n's build up a set, which is called the fusion rules of C. Now, this is important because from these, then you can gain a lot of information on the nature of C itself. Then a modular category is said to be braided if, in addition to the previous property, it is also equipped with this natural morphism, which is if you take the product of two objects and it sends it to the opposite product, this is called the braiding. And so if you want to see this pictorially, it's like saying that you have two strands and they intersect at some point, and C is basically swapping the way in which they intersect. And if you take two simple objects, x and y, you can define an S matrix. And the S matrix is obtained by taking the trace of the composition of twice of these C's, twice of these braidings. And this is the S matrix. So in pictures, this is what I mean. So the braiding is basically you have when you want to define the this is a composition of two of them. Basically, you have two braidings here, but you have this is what I mentioned before, the Hopf link. This is nothing but the S matrix. So each one of them is like an S matrix because you see you have x and y, x star, y star, and you have the morphisms in between them. So basically, you are composing two of them together. And so this is an S matrix, and this is another S matrix element. Okay, as I also write here. So this is important because this encodes information of mutual statistics. Okay, and this is one of the two parts. This is the braiding part. But then there's also the ribbon structure. So these two are basically giving you this is giving you like the S transformations, and then the ribbon structure gives you the T transformations. So you can see there's some kind of relation with the S and T transformation of SL2Z. And this is like very much in physics that the role of S and T transformations in string theory. The reason for that, for this bridge, is because these things that I'm explaining now were first introduced in the context of rational conformal field theories and two-dimensional conformal field theories that were first studied in the language of these categorical structures. And these braidings were used to understand anyons, which we will see later as quasi-particle excitations in these lower dimensional setups. So that's where this formalism first started, but then this can actually be extended to higher dimensions in a very natural way using high categorical structures. Okay, we will see this explicitly. Even this, remember when I said For example, we will see that the higher dimensional version of this in the context of seven-dimensional Chern-Simons theory. So we will see that because that theory lives in the bulk of 6 dimensions n equals 2, superconformal field theory. And when I talked about the defects that live in the bulk, sigma, in that case, I said you're going to have things like Hopf-Links of 3-dimensional surfaces. So in that case, you should think actually of these Hopf-Links as being in between 3-dimensional surfaces. They live in the bulk, and you can, when you perform dimensional reduction, for example, or you gauge, then you can act on these Hopf-Links such that maybe one of them is going to be trivialized, and that is going to affect the spectrum of the operators that lives in the resulting absolute theory. So these pictures are quite recursive in the rest of the slides, even though I'm not going to reproduce them again. Okay, so they're always like an underlying. You always have to keep them in mind. Okay, in that sense. Now, the second part, which is instead the ribbon structure, so this comes because if you take C to be a braided fusion category and you take an element in it, then you can define these two morphisms. So you take X and you compose it with the identity and B, which is a one morphism, and you obtain this sequence. And then you can compose it with C and the identity, and then again, from the identity to B dagger. If you write down what these are in pictures, in pictures, this basically corresponds to the twist operator or topological spin of X. This is basically it. So you start from X at the bottom. This is an element. And then you turn here. You compose it with B dagger, and then you get BX, and then you get back to X. And similarly, you can do with another morphism that has another orientation. So this is basically in pictures, these two equations. So the first line is going to be the picture on the left, and the second line is the picture on the right. So you can try and see it yourself. It actually works. If you compose these morphisms, they actually allow you to build these two graphs here. So these are called the ribbon structures, and this is associated to a T matrix. Okay, before we saw the S matrix for the Hopf-Links, and this is the T matrix description. So this is the T matrix. So the T matrix, as I said, is part of the ribbon graphs. So you have this theta, and T is the matrix in front of the identity. Okay, so it's just a diagonal matrix, essentially. Okay. Now, this part now is going to start with the actual notion of charges. Okay, so I don't know how to remove this, but there's I think there's a line that you can't see. I'm sorry about that, but so what I want here to introduce now is the notion of the charges in the context of this formalism. So if we take a finite group, we can define the quantum double category of the group. And this is a definition that was given first by Liang Kong. I would suggest whoever is interested in the mathematical description of these things, especially in the context of the so-called topological orders that are related to, there's a duality, I should have said, there's a duality in between the symmetry topological field theory that I started describing yesterday, and another thing which is called topological orders. Topological orders have been developed by condensed matter physicists, but also by mathematicians. And there are a lot of papers that have been written by this mathematician, Liang Kong, that are really good, and I would really suggest you to read because they're pure maths papers, but they are inspired by physics applications, and they're great to get this categorical perspective of what charges and conformal field theories are. And so in this setup, you start from an object in this double quantum category, and an object is basically a vector space that is equipped with a G action by this finite group. And this rho is this object, okay? And there's also a G gradient on V. And so this this gives us this raw on G that sends V at H, which is an element of G, to V of GH, G to the minus 1. So this is the object in the category, okay? Then a morphism in DG is a C-linear map that is both a morphism in the representation and a morphism in vet G, which is the trivial representation, basically. And given an element in G, we denote its conjugacy class as G inside square brackets and its centralizer as ZG. Now, if pi is an irreducible ZG representation, then the induced representation is going to be a G representation that admits a G gradient. And this is a simple object in DG. So basically, altogether, the isomorphism classes of the objects are labeled by these pairs. One is the class of G and the other is the class of raw, where one is the conjugacy class and the other is that of the irreducible representations. So you can think of these as being like the electric and magnetic charges. So raw would be like, this class would be, the class of raw would be like the electric charge and the class of G would be like the magnetic charge. So these are dual pairs to each other. Okay, so this is what I mean when I said that this is the categorical description of charges. So whenever you have like M and E, these are like those pairs. But this is in the definition of the categories. Okay. So when I mentioned before the S&T matrices, what they look like, for example, so if you take the S&T matrices to be like the ones of SL2Z group, so they can be defined in this way and they have certain properties. So for example, ST cube is S squared and S4 is equal to 1. So you can map, for example, this to capital S divided by square root of the dimension of the matrix, of the category, and little t to the actual T matrix that we had before. Okay, so this is the S that we had before in the hop link, and this is T in the ribbon graph. Okay, so under this map, you see I mentioned before, this is like the SL2Z that you have in string theory, and these are this S and T are the ones that we had before when describing the braiding and the ribbon structures. So there's a map that you can define in between the two. And once you have that, then you can define the quantum dimension. Now, this is a very important notion because quantum dimensions encode the degrees of freedom, the total degrees of freedom of a certain category. But you can also define them for subcategories of a global category. And the definition of the quantum dimension comes from that of the S matrix, the one in the Hopf-Link description. Yeah. Sorry, there's somebody that wrote down points. What do you mean with that? Okay. Okay, so I think I made a typo here because I wanted to put the identity here. I will edit this, but this is actually meant S at 1xi. Okay, so this is just a typo in LaTeX. Okay, but this is the identity. Okay, so now we turn now we switch gears a little bit here, okay? We start building the connection with physics, which is the whole point of this. So two main examples of higher categories are going to be the main theme from now on. So the first example is Chern-Simons theory. I said this is very important because it's basically the theory that lives in the bulk of the symmetry topological field theory configuration. And the second example is that of string theory and quantum mechanics, as viewed as functorial field theories. Now, these two things are going to probably be the rest of my lectures, these two topics, but spread over different examples, okay? So we're going to see a lot of them. Now, let's start with Chern-Simons theory. So this is the main example of modular tensor category that we will be using. And we can assume that the total category is associated to a theory which admits some gauge group. And this theory is given by a superselection sector, a set of superselection sectors. And these superselection sectors are denoted in this way by convention. So one of them is the category of points. Then you have the category of fluxes, and then the category of Hopf links. Now, what these mean from the physics point of view, they're basically what I referred to as the charges. So you can think of the points as being like the electric charges, flux here as the magnetic charges, and Hopf as being dionic objects, which means particles that have both electric and magnetic charges at the same time. If you act on these, if you act on the theory by gauging a subgroup, this particular configuration of superselection sectors is a consequence of the choice of the gauge group. So this equation is in one-to-one correspondence with G. Once you set G, this equation is given as a consequence of it. So it automatically tells you that you know what the spectrum of operators is and what the partition function is. So if you act on G by gauging, then this configuration is going to reshuffle. In some way, some of the electric charges are going to turn to magnetic or to dionic objects, and also in turn, dionic objects might turn into electric or magnetic, or just rechanging the way in which the electric and magnetic sectors are defined. So the spectrum is going to change, and as a consequence, also the partition function is going to change, which means that the bulk of the symmetry TFT is going to encode different topological sectors in it. Okay. Now, points. Mathematically, these points are, this category of points is going to be a set of objects. Okay, these objects lie in the irreducible representations of G. And these are the point excitations that I mentioned before. So if we want to look at the quantum dimension of this subcategory, we can do that because we have the tool of the S matrix. So we can calculate what that dimension is using the equation that I showed you before. And the quantum dimension is going to be just the dimension of the representation that I'm looking at. For fluxes, so fluxes are going to be the superselection of corresponding to the conjugacy classes that I also mentioned before. When I had the pair, I said I have the pair of classes of ρ and classes of G. I said one is associated to the electric charges that are irreducible representations, and the conjugacy classes are instead the associated to the magnetic charges. So that's what I mean with this. So the conjugacy classes of the finite group here. And the quantum dimension can in turn be calculated in a similar fashion. So I can get the quantum dimension as the square root of C, where C is the number of group elements in that particular conjugacy class. So that's why I keep the mu index here, because this dimension is actually for, I just mean it's the dimension of one particular group element of one particular element in the conjugacy class category. Okay, so I can calculate this for each one of the elements in C flux. Okay. And then for the Hopf link is the collection of all Hopf link excitations. So it's all the dionic objects that live in the theory. So things that have both electric and magnetic charge at the same time. And in this case, the quantum dimension is going to be composed by these things. It's going to be the ratio of G, the rank of G, and EGH, which is defined to be the set of all T's, all elements inside G, such that GH, this pair, is equal to TG, T to the minus 1, TH, T to the minus 1, times the dimension of the representation. So you see there's a combination of all the notions all together, given that the fact that you see that the dimension is carrying information of both the electric and magnetic sectors of the dionic objects. Okay, that's part of the dimension definition. So basically, once you have the dimensions, you know that different objects are going to weigh in a different, they're going to have a different weight because of this different dimensionality. So when you act with a gauging, you would expect that the gauging would also affect the dimensionality of each one of these constituents. In a suitable way. For example, some of them might increase the dimension, the quantum dimension, and some of them might decrease. So this is associated to a possibility of storing some kind of topological quantum information in these superselection sectors in different ways. In fact, I would suggest, I didn't write this down, but I would suggest people to read this very interesting it's quite a long paper, but it's called, I think it's called Knots and Entanglement. And it's a very mathematical paper where you actually appreciate how things like topological entanglement can be stored inside knots of higher dimensional setups, even three-dimensional knots can be stored, and you can calculate things like entropies in that setup. So I would really suggest you to read this paper. It's called Knots and Entanglement by John McGreevy and collaborators. It's like 2 years ago, maybe, yes, 2 or 3 years ago he wrote that. It's in the Condensed Matter Physics archive. Now, once you have these superselection sectors, you can define the one morphisms in between them. So, because that's the whole point, right? When you have in mind that the structure of categories, you always try to define objects and morphisms in between them and higher morphisms. So the same thing we're going to do here. So we have defined the superselection sectors that are like the objects that live in the theory. And then you want to look at how these superselection sectors talk to each other. So, for example, we can define these different morphisms. So one is the embedding of the fluxes inside the loops, and then the loops inside the Hopf. So this is because, of course, the loops, fluxes, I should have said this probably, but you can think I didn't actually write this down apart from, maybe I'll go back. I'll just show you, I have the Hopf link. The Hopf link is like, take, for example, this picture on the left. This is an example of a Hopf link. So objects would actually be, sorry, not, let me put it this way. So elements of the point category would be points. Okay, so say, for example, a point here on this orange line. And that would be the example of an electric charge. The magnetic charge instead would be a loop, sorry, a flux. So this circle, the whole orange circle, forget about the green one, just the orange circle, that would be one element in the category of fluxes, okay? But then you have the Hopf link, which is an element in the dionic sector. So it would be both rings linked together. Now, the category of fluxes would be these circles, one circle alone, but that is embedded inside the whole category of all loops. So obviously, the fact that we have a finite spectrum constrains the fact that we can't identify actually the whole category of fluxes with the whole category of loops. It's got to be an embedding. So you only select a certain subcategory of the whole loop category. So that explains why I'm talking about an embedding here. This is an embedding for that reason. So the category of fluxes is embedded in the category of loops. And in turn, the category of loops is a subcategory of the category of Hopf links. Because you can think of the Hopf links as being, since there are two rings together, you can always trivialize one of the rings and you end up having a loop. Okay, so that's why that. And then you can take another morphism that instead embeds the category of points inside of the category of loops. And you can do that because you can always imagine of shrinking a loop, and that loop is going to give you the point. Okay, so, and in turn, the loop is inside the category of Hopf once more because of the same relation we had before. So these are natural embeddings that you would expect in the spectrum. And obviously you have the automorphism of the Hopf category to itself, which is called by this, denoted conventionally in this way as V. So once more, this is what I already said, but charges are basically obtained as this triple of parameters. You can say that the objects, all objects that live in the original category of the theory, which is this CT that I defined at the beginning, is basically given by this triple of objects. And then these are associated to the charges, okay, that I had before. And they correspond to what is called a flux quasi-particle charge composite, okay? Because flux is the magnetic part, quasi-particles are the dions, and charges are referred to just the electric charges in this context, okay? So that's what I refer to here. And quasi-particles are actually what were originally called anyons that I mentioned, that's the whole setup where this machinery was first developed, okay? So bear in mind that I would suggest you also to read as an additional thing, if you're interested, there's this original paper by Gregory Moore and Nathan Seiberg on two-dimensional rational conformal field theories and the introduction of these anyons and anyon condensations that are needed that were used as first settings to describe these categorical structures for physics, and then were developed in higher dimensional setups and more extended situations. But that's where actually where this started off as a way to understand mathematically the behavior of anyons that are these quasi-particles that I mentioned here. Okay, so this is a little bit more of history, I would say. So applications of categories in physics, as I said, began in 2 dimensions and then was extended in higher dimensions, mostly because one wanted to understand how to describe quantum field theories because of what we said before. So we know that topological field theories live at the boundary of a one-dimensional lower quantum field theory, and this is a proof by, I mean, it's a proof from the point of view of highly supersymmetric theories. We know that there's a theorem that states that that's true. It's the Milnor theorem. But apart from that, there's this machinery of symmetry topological field theories that we know to be true based on cobordism theories. And the pioneering work of Moore and Seiberg on modular tensor categories, and then also by Reshetikhin and Turaev, reformulated this in the context of rational topological quantum field theories and topological orders. So these topological orders are going to be important later on in the course. Basically, you can think of topological orders as being lower dimensional setting where the algebraic structure of the categories that live in the the algebraic structure of the symmetry topological field theory that lives in the bulk of the quantum field theory can be mapped to. So the advantage of the topological order picture is that being lower dimensional, it gives you a chance to better understand, even imagining how the network of categorical relations actually give you the resulting physics that you want to study. Okay, we will see this in explicit example, but I guess that you can appreciate the fact that lower dimensional setups have the advantage that they are much easier to conceive from just, an intuition, from the intuitive perspective. So as I mentioned also before, anyons are quasi-particles. So whenever I talk about anyons, I always mean quasi-particles that are these like dionic objects, okay? And systems that behave with the anyon symmetries with certain gauge group G are known to be effectively described by Chern-Simons theory. Now, what is Chern-Simons theory? I said it's that it lives usually in the bulk in this symmetry topological field theory, it's the theory in the bulk. This is the physics behind the categories that I mentioned earlier. So for this correspondence to hold, though, we need to require that this physical theory, the Chern-Simons theory, it has to account for all the topological information that the Braden statistics encodes. So all the S matrix structures and that we described before with the Hopflings, it needs to be encoded automatically in this physics theory that we choose to live in the bulk of the quantum field theory in question. So we need to write down effectively some partition function for the bulk and its corresponding action from which we derive it, such that the Braden structure is automatically encoded in it. Okay, so the partition function is going to be, as I mentioned, it's a path integral over the fields of the exponential of I action j, where j is the sources. Okay, and this is going to involve U1 gauge fields that are this set of fields, A1 to AN, alpha 1 to alpha n. And this is the corresponding action. So I'm going to have the first term is the usual Chern-Simons term that is always there. And then you have an additional term with the sources, these J's that are the sources. Now, these quasi-particles that I mentioned earlier are the sources for these J's that live in the bulk theory, and they are labeled. They take these labelings, these quasi-particles, on a lattice, and at long distance, these form basically single entities. So this is why you can think of them as actually giving rise to a fusion structure. Okay, so the anyons would otherwise be something like, you can think of them as being like lines that at endpoints have two particles. Okay, so it's like saying that they are at the same time point particles and fluxes. Okay, so in that sense, they are dionic. So if you imagine them as strings that at the endpoints have two spheres. And so these things at close distance, they are, when you're very close to them, they are actually extended. But then if you go very far away, they just end up being points. And if they are just points, then you can define the composition just as being the composition of points. So it makes sense to use the notion of fusion structures and fusion categories to describe even such a setup. So that explains why this picture of Chern-Simons adapted to this allows you to describe effectively a mathematical theory, which is that of fusion categories, which is the main tool that we're using in this context. Okay. And there's also an additional thing here, this K in front of the Chern-Simons term. This K is basically this K matrix that dictates the Braden. Okay, so when I said before that the Chern-Simons theory needs to be chosen accordingly, such that the Braden is accounted for automatically in a suitable way, this is what this K is for here. Okay, so K is defined from the S matrix. So we had the S matrix defined as earlier on, and the S matrix is related to K by this equation, where D is basically the total quantum dimension of the superselection sector that we're looking at in this case. Okay. In this case, this is for the whole theory, so D is going to be the total quantum dimension of all superselection sectors altogether. And A is going to be the associated algebra of that superselection sector. Now, K is also related to the T, to the ribbon structure by this other equation. Okay, and this is because we need both. Okay, we need both S and T for it to be defined. And this is this topological phase, this theta is a topological phase essentially, and it's generated by the ionic symmetries, and it's also referred to as twisted liquid in the literature, mostly in the condensed matter literature. And this is a generalization of a three-dimensional discrete gauge theory. Okay, And the total quantum dimension, basically, when you perform the gauging, as I mentioned, is going to change in some way, which is expected to be like as the following. So if you have the topological liquid, the quantum dimension of the topological liquid is supposed to be equal to the quantum dimension before gauging and that and the rank of the gauge group G. So this is because if you perform the gauging, you're expecting, unless you have some other sector, that there's going to be a loss of degrees of freedom. That's associated to the idea that if you have as I mentioned before, you have this map mu that goes from an N fusion category that you select to a gauged algebra, which is then mapped to the identity in the new theory, in the resultant absolute theory. So that trivialization of a subalgebra is due to the gauging that you perform. So that is automatically from the point of view of the total quantum dimension, that is going to tell you that there's going to be some degrees of freedom that are lost. And this is what this equation is telling you. But it actually happens that there are situations that are non-trivial, in which case instead there might be other superselection sectors that you didn't account for that instead might store those additional degrees of freedom that you might have thought that were going to be removed altogether. So that's where things are more interesting. So it's not just, so this is not accounting for all cases. This is what I want to stress. Okay, this equation 106 is a very particular example where the gauging leads to trivialization and loss of degrees of freedom. But there are cases where this is not the case, where the gauging actually opens for the chance of new superselection sectors to be filled with those degrees of freedom. Okay. So you see, if you want to build, even at this level already, connection with physics, you can see that you might think, what does this mean? Might this mean that there's some kind of new particles that are arising? Or are there, other things that have not been thought about or that arise from the beginning before doing any gauging? Maybe we needed to understand the theory before the gauging to see whether these possible new superselection sectors could arise. So this is the whole spirit why I'm saying this, okay? Now we turn to the second case, which is string theory. Now, this is, as a whole, it's, don't take this as the ultimate, so maybe I would say this. Maybe I would suggest to break for a few minutes now because
Please go ahead.
we can start if you want.
Yeah.
Okay, so now we turn to the second example. So the first example, I said it's the Chern-Simons theory. We will see a particular example of that later on. But now we'll give you motivations for looking at string theory as a categorical theory and in a functorial way, especially. So this is not, as I mentioned, it's not something that is completely understood, and it's still a matter of study, including my own research. So this is not at all the last word on the topic. But I want to introduce you to this if you haven't heard about it before, because I think it's a very promising direction for understanding where unification of fundamental interactions might lead to groundbreaking results. Okay, so. So string theory can be understood as some kind of puncture in between two categories. One is the category of cobordisms, and the other is category of vect. So the category of vect is that of vector spaces that describes the quantum states of string theory. And cobordisms, we're going to see them in more detail later, and because they are related to the space-time geometry of strings. And the functorial approach can be used to both encode in this setup quantum field theory and quantum mechanics. Quantum mechanics can be thought of as a very particular limit of quantum field theory, and quantum field theory is the one that we've tried to describe earlier with the symmetry TFT, okay? Of course, as I said, there's the big issue of relating different theories, like different interactions together. We still don't know how to do that, but if we take just one particular interaction, then there's a way to understand how those things can be done, okay, with good control from the mathematical point of view. But the most important and subtle part of this is to completely identify the two categories that you see in this expression. This is a highly non-trivial thing. The advantage is that, as you can see, these are just two-dimensional, these are two categories, which means that you just need to define objects and morphisms. And two morphisms are quite easy to determine also. So it's not too bad, but the thing is that the structure that underlies these two categories is something that at some point gets to some obstruction. You get some obstructions due to when you start using it from a physical point of view. And those obstructions are interesting because they tell you that the maths needs to be developed even further. So we're going to see that explicitly. And the important thing is that this functor actually allows you to describe higher dimensional theories without the need to actually think about them as higher dimensional objects. You can just push them down to lower dimensional things that you can actually see them and draw them in a convenient way. We will see these all later. This is just to give you an idea of what I mean. So this is a picture. You can think of strings as being these red circles, okay? And the cobordism in between them is the blue part. So this bulk is encoding, it is a surface with genus, okay? So the genus here is totally arbitrary, but it's just to tell you that the cobordism that connects the red strings is something that encodes the information that you need to define the high dimensional theory. Because if you know that, for example, the choice of the Calabi-Yau, when you perform dimensional reduction from 10-dimensional string theory, the choice of the Calabi-Yau tells you what is going to be the field content of the theory in the 4-dimensional resultant theory, because of the Hodge structure that you choose, because of the topology of the Calabi-Yau, they're all elements, all data that are going to lead to a particular choice of the spectrum of operators. So that topological notion is the same as this topological notion that you have encoded in this picture that tells you what is the resultant theory in coming from the string theory where these red circles live. Okay, so the red circles are the string theory, and the cobordism encodes the topology that then in turn gives you the resultant spectrum that lives in the string theory in the higher dimensional picture, which is not drawn here. Okay. Now, this is just a diagram. I'm pretty sure you might have seen this before. This is a diagram synthesizing how the different string theories relate to each other. And it's nice to see how these are related by S and T transformations. So this is just to mention that the different string theories that have been proposed so far as possible candidates for unifying theories, they're all related in this way that are by means of dualities. So this is why dualities are so important, and why having solid mathematical tool to study dualities is also a significant thing to have, because there are some cases where calculations are easier to perform in one setup rather than the other. But then if you know how to map the calculations that you've done in one particular sector to the other, then basically it's much easier. It makes things easier to do. And in turn, if you want to understand the mathematical structure, then you should also understand how the dualities translate as mathematical properties from a categorical point of view. So these are all things that motivate the use of high categorical structures to understand quantum field theories that arise from possible dimensional reductions of string theory. And the mother theory of all is M theory, which is a higher dimensional. It's not 10 dimensions, it's 11 dimensional, but it's at the heart of this understanding, because as we will see, M theory is related to the 6-dimensional n equals 2 superconformal field theory that we can start with. That is the higher supersymmetric theory that we can deal with. And that theory is well known from the maths point of view. So we have good mathematical control of that. And we would aim to achieve a lower dimensional theory, possibly without supersymmetry, to understand what the mathematical structure is. So this is all in view of the motivation of why this is an important thing to understand. So if we want to look at quantum mechanics, I think yesterday somebody asked about this, but so quantum mechanics is a particular example of a quantum field theory. I would say maybe I would just give you this short digression. I would say that if you haven't studied quantum mechanics or quantum field theory, I would say that it's important to bear in mind that even if the two are related, there's still a lot of open questions in this regard. So it's a highly non-trivial statement to state that quantum mechanics is a particular example of quantum field theory, because at present we don't know how to relate the two effectively. There are, for example, I'll give you an example. There's this literature by Witten and collaborators that they deal with von Neumann algebras, and they express how to go, for example, from type 3 von Neumann algebras to type 2 one. And that's by turning on gravity. But then there's the problem of going to type 1, which still people don't know how to do that. And type 1 is a quantum mechanics, okay? So this is just to state that we expect quantum mechanics to be a particular subsector of quantum field theory, but given that we don't have mathematical control of quantum field theory yet as a whole, we can't actually state how quantum mechanics is exactly embedded mathematically in quantum field theory, because quantum mechanics can be totally predicted, and it has a very simple mathematical formulation, which is not like the one that we have from the point of view of quantum field theory. So the obvious aim is that of bridging in between the two, but we're still far from that. So this statement that that quantum mechanics is a subset of quantum field theory is actually a very strong one and still needs to be proved. Okay. Quantum mechanics is basically described by a set of possible quantum states of particle, and these states are the states that I mentioned, I think, yesterday when I talked about amplitudes, and I said the amplitude is basically an expectation value that you calculate on some states. And the original assumption, the usual assumption, if you're not told otherwise, is that the calculation is done on the ground state. That is assuming that you have potential that has a minimum, so it emits a minimum energy level, and the vacuum is the eigenvalue of that energy level. Now, yes, so the excited states are going to be particle excitations that you build by acting with creation operators on the ground state. So these are what these quantum states are when I talk about quantum states in quantum mechanics. And in addition to states, you need to define sets of operators. And these operators are conventionally noted by this U, T, and this T is just a real number. You can think of this as time, like time evolution. That's why, because quantum mechanics is just, function of time. You can also assign, obviously, a space dependence to the wave function. But this T is actually just telling you the time evolution of the operators, which is the only thing that really matters in quantum mechanics. So you can build a composition law in between these operators, and there's a linearity in the dependence on time. So if you compose two operators that have different time parameterization, then the resulting operator is going to be given by the sum by a new operator with the time parameterization given by the sum of the two. Okay, so this is so if you start at a certain time, you're going to end up having the time that is equal to the sum of the two times. So this is quite a simple. You can see it's you can appreciate it's quite a simple description. But now we can turn to a more interesting thing, which is where we want to go, which is towards string theory. Now, one of the things that has been, if you assume, I stress, I'm assuming that string theory is the best candidate up to date for obtaining a unifying theory of fundamental interactions. So we assume that Calabi-Yaos are the manifolds on which we should dimensionally reduce 10-dimensional string theory to obtain a 4-dimensional world as the one where we live. So we should think of every point in space-time where we live as being actually the Calabi-Yau on which we've dimensionally reduced the 10-dimensional theory. Now, from a mathematical point of view, these Calabi-Yaus are associated to categories, which then have been conventionally called just Calabi-Yau categories. And examples of these Calabi-Yau categories are the Calabi-Yau varieties that are used in these model buildings from top down. And also another important class, which are Fukaya categories that are associated with symplectic manifolds. Now, this is a whole topic on its own. I'm not going to go too much into that, but this is, for example, in the context of homological mirror symmetry. So this is where dualities come up and start acquiring importance in this study. I just wanted to mention it in this lecture. I'm not going to deal with it, but it's just to mention that dualities are a very important tool to study in maths because they allow you to have more insights in physics. So they can be analyzed, they can be studied. Dualities can be studied in the context of categories, and Fukaya was one of the first people that addressed this topic and was used in the context of homological mirror symmetry, which in turn was motivated by a physics conjecture. So you see that these things are very much related to each other. So it's important that the fields keep on motivating each other, because they can actually lead to important and significant advancements in either side. Now, just to give you a definition of what Calabi-Yau categories are, so you can see the structure is very similar to what we saw before. So you have it's a category that is equipped with a trace-like map. So you take two objects and you trace, and this gives you a ground field. And then there's also an induced pairing, and this pairing is denoted in this way. And this trace has got to be symmetric and non-degenerate. So this is the definition of Calabi-Yau category. So this is just a diagram just to show you where we're going next. So we talked about high categorical structures in the symmetry topological field theory setup, and we discussed how these can be used as describing the topological quantum field theories that live in the bulk of a relative quantum field theory. But at the same time, we can use this to describe string theory, and we will see why this is the case next. But also, high categorical structures are very useful for describing quiver gauge theories by means of algebraic geometry, which is also going to be another thing that we're going to deal with later on in the course, maybe last lecture or so. But now, for the time being, we're going to start with the first part, okay? So if people don't know what quivers are, quivers are basically diagrams that if you have a gauge theory, they are all different gauge theories that interact with each other. A quiver is just a diagram that shows you how to not describe, but let's say it's a concise way of drawing in a pictorial way, what are the interactions in between the fields that you can write down in a Lagrangian. So if you have a Lagrangian and you have interactions in between fields, there's going to be a corresponding potential associated to that, and the potential is basically the interaction term. And those interactions can be mapped to a diagram, which is called the quiver. So this is what I mean by that. And it can be used also in the case of, for example, there's been recent progress in understanding how to embed the quiver of the minimally supersymmetric standard model in string theory. So quivers also arise in that case, but quivers arise also in the context of brainwebs, for example, if you've heard about them. We will see that in detail, but you start from highly supersymmetric settings and you can write down the quiver for that. And then you perform supersymmetry breaking on the quiver and you see what the quiver is going to look like. So that's going to be giving you some superpotential, and you can study the superpotential. It's going to give you the interactions in between the fields, and that is a way of keeping track of the field content and the interactions involved, so also the symmetries that are involved in the theory. So now we start this part on quivers, but before quivers, we are going to go through long digression. So this is a map that I'm going to come to later. I will skip it for the moment, but I wanted to put it here just for you to see, because so there are many things that we're going to touch here, but it's good that you told me. I didn't think about it. Okay, so this diagram is I'm not going to explain all the diagram now, but this I just wanted to put it because I'm going to come back to it in the next lectures. Okay, so this is just to have it here. For the moment, I can just tell you the following. So where are we at the moment? I explained this basically, symmetry TFTs. So I've explained just a little bit of the whole diagram. And this thing, symmetry TFTs and topological orders, I mentioned this, but we're going to come back to this later. So we're going to see all the rest, more or less, okay? So there's a lot to be understood yet, but this is the plan. So we've seen symmetry TFTs, and I explained very briefly what topological orders are. They're basically there's this duality that you can build in between high dimensional symmetry TFTs and lower dimensional topological orders that are easier to describe from, mathematically and pictorially. And you can describe the algebra of the defects that live in the symmetry TFT by means of the algebras that live in the topological orders. And these are described in Liang Kong's papers that I quoted before. Now, topological orders can be the useful setup for describing factorization homology. We will see this in great detail, and it's a very important mathematical tool from the particle physics perspective, because they allow you to actually calculate things from the point of view of the dimension. When I talked before about the dimension, when you perform the gauging, how the quantum dimension is affected by the gauging process, factorization homology is an alternative way of calculating that. And in particular, it's important to do that if you aim at achieving setups where to describe dualities. So if you want to have a duality in between two theories that are dual to each other, we've seen before how dualities are important for string theory. They build a web. Okay, so we would like to see how these dualities are related to each other and how they are described mathematically. So factorization homology provides us a tool to do that. Okay, so we will see how that is actually done concretely. And they are just calculations that you do in 2 dimensions, okay, even if the theories are high dimensional. So that's the advantage of that. And that's why I have this arrow that bridges in between 2-dimensional TFTs and factorization homology, because they are 2-dimensional, actually. Now, 2-dimensional TFTs are essentially the functor that I had before. When I said string theory can be described as a map, curly F from the cobordism to the vector category, that map, the map itself is a two-dimensional TFT. Okay, so we will see this explicitly, and this is crucial for the string theory point of view because you can encode in a two-dimensional TFT the notion of D-branes, for example, that are extended objects, and they carry the notion of the fluxes and the charges and everything that lives in the theory that you want to study. Okay, so if you want to have good control of the resultant theory that is obtained, that is assigned from a given choice of a string theory, you need to know and have full control of the categories that define this two-dimensional TFT. And this is what was originally studied by Moore and Tachikawa, that followed up as a physics paper from a more maths-oriented paper by Moore and Segal on Bordism operators and Bordism categories. So this is basically just to say why we're doing this, and I hope that this encourages you towards the motivations for studying this topic, or just following what I'm going to say in the next few lectures. Okay. The rest of the diagram, I'm probably going to touch it very briefly. I don't have enough time, but hopefully I will be able to at least explain this part here, which is the main building block of these lectures. Okay. These are other possible directions that you can study in turn. Okay. Okay, so this is just to write down some motivations, this just for you to bear in mind. So, so the setups that we're going to be dealing with now for the rest of the lectures, I want to stress they're going to be highly supersymmetric. I know that some people yesterday asked me if we're going to see anything like the gauge structures in Hilbert series for effective field theories. As I mentioned yesterday, I don't think that I am, I'm not sure that I will be able to do that for a matter of time. I will try to get there, but my approach is my approach is top down. So the question that was raised yesterday is actually a request of a bottom-up approach, which goes slightly differently from all the machinery that I'm building with these lectures. So if I manage to get there, I will try to say something, but I won't make it the main purpose of my lectures. I hope that's okay. But I would strongly suggest you to read. I would strongly suggest you to read literature in that regard. If I don't manage to get there, I will eventually recommend some literature, but there is a vast literature on the application of and calculations of Hilbert series for effective field theories that have been amply developed, especially in minimally supersymmetric standard models. So there's a lot that can be studied in that context, but it goes a little bit beyond what my setups are, which are highly supersymmetric theories and supersymmetry breaking of those, but not yet without supersymmetry. Okay. So so the purpose of this part is going to be that of highlighting features in categorical structures of supersymmetric gauge theories that could come, the formalisms could come as aid towards furthering the understanding of the standard model, albeit we're not there. So this is, I want to stress, we're not there yet, but I believe that this machinery still needs to be developed and could be potentially very useful for that. So also, as I also said before, the quiver description of the standard model is known, and we know how to embed that in string theory. So given that there's a good possibility, I mean, the minimally supersymmetric standard model quiver, we know how to embed that in string theory. So given that, we could try and find a way of bridging the mathematical machinery describing highly supersymmetric theories towards the minimally supersymmetric standard model using category theory, which is still to be done. Okay, this is not done yet. And potentially somebody could then use the bottom-up approach and see what the corresponding effective field theory would be if that gives us some additional information in that regard. So what we're going to do next is, in the following lectures, is First of all, we're going to review some key features about equivariant cohomology. We're going to see what that is, and the convolution product, because we need this in the context of quiver gauge theories, okay, for defining, for example, Coulomb branches. And then we're going to introduce the more Tachikawa varieties that I had in the diagram, because they are that particular two-dimensional topological field theory that we need to describe the higher dimensional picture. And then we're going to highlight the importance of the notion of abelianization to embed ring homologies for the theory in question, and how this is related to ungauging of categorical symmetry TFTs. So this is, I stress, this is a very particular choice of dealing with these topics. I'm not saying that this is the only way. There might be different, but this is just a consequence of what I studied during my PhD. So that's why I'm touching these particular topics. So first, we're going to go through quite a long digression of just mathematical preliminaries, okay? And then we're going to get to the physics later on, probably from next lecture on. So we're going to start off now with cochain level theories. So motivation for this is that cochain level theories are very important in the context of highly supersymmetric theories, such as 6D n equals 2. So I often mention this, but this is actually as I said, it's the highest supersymmetric theory that we have in physics. And from that, we can build a whole diagram of lower dimensional theories with lower supersymmetry that are related by dualities in turn. So studying the cochain level theories under dimensional reduction and under supersymmetry breaking gives us a good control of the mathematical structure that underlies the theory in question. So this is why this is so important. So we start off with a definition of cochain complexes. So a cochain complex is a pair that is built up of a sequence of abelian groups, these A's, and a sequence of homomorphisms in between consecutive groups, such that the image of each homomorphism is in the kernel of the next. So to each pair, this is an associated homology that describes how the images are included in the kernels. And you can define the nth homology group to be just the ratio between the kernel of Dn and the image of Dn plus 1. Now, in the context of strings, you can do the same thing by replacing D with Q, which is the BRST operator. Now, it doesn't matter if you don't know what that is, but just keep this as a definition. So the BRST operator is an operator that maps the chain complex to itself, such that Q squares to 0. So you see there's the same properties as D squared, right? So that's why this makes sense from a maths point of view. It makes sense to define such a quantity. So, but this is to tell you why this is an important element to be an important tool to be used even in the context of string theory. Now we turn to dualities. So I said before that dualities are important for many reasons in physics, because they, especially in the context of string theory, they can allow you to connect in between different string theory models. And we want to find a tool where to study this, how to study this. And we talked about the quantum dimension, and the quantum dimension is important to keep track of the gauged sectors of the theory and how the degrees of freedom are reduced under gauging. So we want to find actually something that gives us control of the theory, and it's not just the quantum dimension. We actually want to find a more articulated structure that gives us access to the higher categorical structure of the gauged theory. We want to keep track of the objects, the morphisms, etc. Okay. So this is why we introduced the factorization homology, which is one of the entries in the diagram that I showed you before. So factorization homology satisfies some properties, and it's basically defined in this way. So it's a pair given by the Hilbert space H of a certain topological order and the ground state degeneracy, which I call U sigma. Now this is obtained by integrating over M, which is the manifold in question, which is the topological order. Okay, I'm integrating over it A, and A is the algebra that encodes in the topological order. It encodes the higher categorical structure of the corresponding symmetry TFT that I was looking at in the definition I gave you yesterday. Okay, so I said there's this correspondence in between topological orders and symmetry TFTs, and the advantage of the topological order is that it's lower dimensional, so you can map even a higher dimensional symmetry TFT to a two-dimensional topological order by choosing and defining a suitable algebra, this curly A, that encodes the higher categorical structure of the bulk symmetry TFT. So if you know that, then this integral gives you this pair of Hilbert space of the topological order and the ground state degeneracy. So you see there's more structure than just the dimension, the quantum dimension that I defined earlier on. It's a richer structure. And so given that, it allows you to study more interesting physics setups. So basically this is the only global observable that you can define. So this is why this definition is as such. So you can these are the only things that you can actually define on this topological order. Okay, so the Hilbert space is supposed to be the space where all the states live. For those of you who don't know in the physics context, that's what I mean by that. So it means both ground state and excited states. It's not changing. Oh, okay. Now on this topological order, you can also define a fully faithful functor, which is this math frac Z, which is basically the Drinfeld center. Okay, so this is, if you remember when I mentioned today earlier on, an absolute theory is defined by three parts. Okay, a triple of maps. I said you have the I'm trying to remember the order. I had the fiber functor, the moment map, and the Drinfeld center. So F, mu, and Z. So I said if you have any of these three, then you can find the other. And in this context, the context of topological orders, the Drinfeld center, which is this Z, it's the natural thing to define, and it acts on objects and morphisms. Okay, so it acts on the category itself to give you the Drinfeld center of the category. So it gives you the notion of the identity, or let's say better, it's the endomorphism of the identity of the category that I defined earlier on. And it also acts on the morphisms, because I can have C and D to be two different categories, and M, which is the morphism in between them. And so I'm bridging in between two categories, and I can act on this morphism with the Drinfeld center itself, and it gives me a functor of the functor of the morphism itself. So it's the identity of the morphism. So for the category C that I started with to be a modular tensor category, this needs to satisfy this condition. So I need to have that the Drinfeld center of C needs to be like the category tensored with C opposite. So I'm basically taking the reverse of C and composed with C itself, it's got to give me back the identity. Now, let me see, maybe this... Okay, so basically here I'm just saying that you can extend this for in higher dimensions, but it's okay, maybe this is not the moment to put this right now. Let me just skip this for the moment. I'll skip it for a second. So let's go to this, which is going more in depth into the definition of this algebra, when I have this algebra defined in here. So this algebra here, we need to define this. So we want to find the right-hand side, which is the Hilbert space and the ground state degeneracy. But we need to do that, we need to define what A is. And if you define A, it means that you know what the higher categorical structure of the bulk symmetry TFT is, okay? And so we need to find, so it's a two-dimensional topological order. So it means we need to define objects, we need to define morphisms and two morphisms, okay? So it's a triple. This algebra is a triple. So the algebra here is basically a map in turn in between oriented disks and B, which is an n-disk algebra. So basically you're trying this map has got different levels of structure. Okay, it's not just a one level structure. And in particular, you can write this down as this map. But maybe this is too much to be said at the moment. We can say the following. You can say that A, let me go, I'll just go ahead and then I'll come back. But if you have like this, I'll give you an example of a stratified factorization homology. So you can think of a factorization homology in between two different categories. So say that you have this picture, you have the green, which is the original category, and then you have the blue, which is the new category. So you have C and D. So C and D, and then you have M, which is the morphism in between them. So you draw it as a line, a circle, oriented circle, that is separating C and D. So it's like having two different phases. One is obtained by gauging. Okay, for example, you start from C. C is associated to some symmetry TFT that has a given gauge group G, and you take away part of that, you gauge part of that gauge group away, and you obtain a new theory, say D, okay? And the two are obviously going to be characterized by different algebraic structures because the gauging has changed the spectrum, and the spectrum has in turn changed the topological structure of the symmetry TFT that is associated to each topological order. So the corresponding morphism that is relating the two is this red line, which is the gauging process that you've performed. Now, on top of that, so this would be, C would be the extended two-dimensional surfaces and D the same. M is one-dimensional. And then you can also define zero cells, which are points. And points are going to be pairs of objects, okay? They're going to be denoted by two things. One is like the categorical, and the other is the dimension. So once you have this, then you can define from that picture, you can define the algebra. So the whole algebra is a triple. It's going to be made of two cells, one cells, and zero cells, because they are either extended like C and D, that are the theories that I deal with. One is the ungauged and the other is the gauged theory. Then I have the one morphism, which is just the line. And then I have the zero cells that are points. So it's these pairs. I have two pairs, for example, that I defined. I could have chosen something else. I could have chosen different points, okay? This is just arbitrary, totally arbitrary. But obviously, arbitrary up to some point. I mean, arbitrary in the sense that this choice of triple actually corresponds to the topological structure that I had in the symmetry TFT. So this has to respect that higher categorical structure that I started with. Okay. And so this is basically the definition that you would get for A in the easiest example, where you have the gauging that just one gauging that allows you to go from a certain symmetry TFT to another. But this is just brought down to just a two-dimensional description, whereas the symmetry TFT could have been any dimension. Okay, just as long as you keep track of the richness of the high categorical structure with this two-dimensional algebra in a suitable way. The other case instead is the non-contractible case, which means when we had before this picture, the fact that C and D were related just by a one gauging step, which means I gauge part of a subgroup in C to get D. That means that I can always go back to the original theory by ungauging, which means that it's corresponding to saying that I contract M, I contract the circle, the red circle, and I get back to C. And the point in the middle would just be the identity at that point, which would be nothing. No, it's not going to affect the algebra in any effective way. So I get back just to having the original theory. That is what I mean by contractible loops. Okay, contractible loops are between two-dimensional topological orders that are separated just by a one gauging step. But there are cases where things are more interesting and loops are non-contractible. So in that case, then you wouldn't have the zero cells anymore, which means that you can only define the two cells and the one cells, so objects and morphisms, but not the two morphisms, which means that loops are not contractible, because if they were contractible, they would give you something that is the identity, but this non-contractibility means that at the point you would get something highly non-trivial. And that highly non-trivial thing would be an algebraic structure with a high categorical feature of its own that you need to study. So that's what I mean by this notion. And this is where the things are more important, are more interesting even from a physics point of view. So they're very interesting for that. And that's where the source of the duality comes in. Okay, that's the case where non-contractible loops arise is where dualities arise, okay, in physics. So I think I would stop there. I would just add another thing, that in the contractible loop case, if you take the dimension of the endomorphism of the identity, it's going to be 1. Whereas if you have the non-contractible loops, the dimension of the endomorphism of the identity is going to be bigger than 1. So that's why it relates to the quantum dimension of the superselection sectors that I defined before today. So I think I'll stop here today and I'll take questions.